Subscribe to the channel so you don't miss out on any of these videos. Imagine a world unlike anything you've ever known, a planet where gravity pulls harder than Earth, where alien skies might glow with unknown hues, and where the ground could be rocky, gaseous, or even covered in oceans deeper than you can fathom. These strange new worlds, called super-Earths and mini-Neptunes, are rewriting what we thought we knew about planets, solar systems, and the very nature of existence. Why haven't we found anything quite like them in our own cosmic backyard? And what secrets might they hold about how planets are born and how life could evolve under wildly different conditions? Let's explore these mysterious worlds that are somewhere between Earth and Neptune in size, composition, and atmosphere. They defy our neat categories of rocky worlds like Earth and Venus or gas giants like Jupiter and Saturn. Yet they're out there in huge numbers, orbiting other stars, and offering us a glimpse into the possibilities of the cosmos. Super-Earths and mini-Neptunes occupy this fascinating middle ground. They're bigger than Earth but smaller than Neptune, and the sheer variety among them is staggering. Some might be rocky, with thick atmospheres that trap heat like a greenhouse gone wild. Others could be icy or water-rich, with vast global oceans and dense clouds. A few might even challenge our ideas about habitability, presenting conditions that could allow alien life to thrive. But what exactly are these worlds, and why are scientists so captivated by them? Here's the kicker: we don't have anything like a super-Earth or a mini-Neptune in our own solar system. Earth is the largest rocky planet here, and Neptune is the smallest ice giant. That gap in size and composition is so sharp in our system, yet in other solar systems, these middle-sized planets seem to be everywhere. They're not just common, they dominate. In fact, they're the most frequently observed types of exoplanets. This raises a big question: why doesn't our solar system have them, and what does that say about us? Scientists think super-Earths and mini-Neptunes could reveal some of the biggest mysteries about how planets form and evolve. Are they failed gas giants that couldn't accumulate enough material to become like Jupiter or Saturn? Are they oversized rocky worlds that gathered thick atmospheres but stopped short of becoming ice giants? Or are they something else entirely, a class of planet we never even imagined before we started finding them? To answer those questions, we need to dig into how planets come together in the first place. Imagine a young star surrounded by a swirling disk of gas and dust, a cosmic construction site where planets begin to take shape. Within this disk, particles collide and stick together, gradually growing into larger and larger bodies. But here's where things get tricky. The amount of material available, the distance from the star, and even the interactions between forming planets can drastically change the outcome. Super-Earths and mini-Neptunes might form in regions of the disk where conditions allow for a perfect balance. Too much material for a small rocky planet like Earth, but not enough for a giant like Neptune. But these planets don't just form and stay put. They can migrate, moving closer or farther from their parent star over time. This migration can drastically alter their atmospheres, compositions, and potential for hosting life. For instance, a mini-Neptune that starts far from its star might migrate inward, its thick gaseous envelope shrinking under the intense heat, leaving behind something closer to a super-Earth. Understanding this dynamic evolution is like piecing together a cosmic puzzle. Now let's talk about what makes these worlds so different from anything we know. First, their atmospheres. Many mini-Neptunes are believed to have thick hydrogen and helium atmospheres, remnants of the primordial gas from the early solar system. These atmospheres might trap enormous amounts of heat, creating conditions we can barely imagine. On the other hand, some super-Earths might have thinner atmospheres, with compositions rich in carbon dioxide, nitrogen, or even water vapor. Speaking of water, some super-Earths and mini-Neptunes could be water worlds, covered entirely by global oceans. Imagine a planet where there's no land, just endless, deep seas stretching for thousands of kilometers. The pressure at the bottom of these oceans would be so immense that exotic forms of ice, unlike anything on Earth, could form. These worlds challenge our understanding of what it means to be habitable. Could life exist in such oceans, perhaps thriving in the darkness near hydrothermal vents? It's not just science fiction. Our own oceans on Earth are teeming with life in places where sunlight never reaches. The more we study these planets, the more questions arise. For instance, why are super-Earths so common in other solar systems, but completely absent here? Some scientists think it might have to do with how Jupiter and Saturn formed. These massive gas giants may have disrupted the early solar system, scattering material and preventing the formation of medium-sized planets. If that's true, it means our solar system is something of an oddball, a cosmic exception rather than the rule. But beyond the scientific intrigue, super-Earths and mini-Neptunes stir something deeper, a sense of possibility. These planets expand our horizons, showing us that the universe is far stranger and more diverse than we ever imagined. They remind us that our Earth, with its perfect balance of size, composition, and distance from the Sun, might not be the only cradle for life. There could be other worlds, circling distant stars, where life has taken root in forms we can't yet comprehend. As telescopes become more powerful, our understanding of these strange new worlds will only deepen. Instruments like the James Webb Space Telescope are already giving us a closer look at their atmospheres, compositions, and even weather patterns. One day, we might find a super-Earth or a mini-Neptune with conditions strikingly similar to Earth, or shockingly alien. And when we do, it will force us to confront the biggest question of all: are we alone in the universe? But for now, the mystery of super-Earths and mini-Neptunes is a reminder that the cosmos is full of surprises. These planets don't just rewrite the rules of planetary science, they ignite our imagination, showing us that the universe is bigger, stranger, and more wonderful than we ever dared to dream. The discovery of super-Earths and mini-Neptunes has fundamentally changed how we think about planets and planetary systems. To truly grasp the importance of these worlds, we need to dive deeper into what makes them so unique and why they could hold the key to understanding our place in the universe. Let's explore their peculiar characteristics, their diversity, and the tools we use to uncover their secrets. One of the most intriguing aspects of super-Earths and mini-Neptunes is their staggering variety. Not all super-Earths are the same, nor are all mini-Neptunes. Some super-Earths are rocky, with solid surfaces that might resemble Earth or Venus. Others might have thick atmospheres that make their conditions closer to a boiling inferno, with surface pressures so high they could crush any human-made object. Meanwhile, mini-Neptunes are thought to be more gaseous, with large envelopes of hydrogen and helium. But even here, the variations are endless. Some mini-Neptunes could have rocky cores surrounded by dense gases, while others might contain large quantities of water, creating exotic layers of high-pressure ice. This diversity makes studying these planets a challenge. When scientists detect a new super-Earth or mini-Neptune, they have to rely on indirect methods to infer what these worlds might be like. Two of the most common methods are the transit method and the radial velocity method. The transit method involves observing the slight dimming of a star as a planet passes in front of it. By measuring how much light the planet blocks, scientists can estimate its size. They can also study the starlight that passes through the planet's atmosphere during a transit, revealing clues about its composition. For instance, if the atmosphere contains water vapor, methane, or carbon dioxide, these molecules leave distinct signatures in the light spectrum. The radial velocity method, on the other hand, measures the tiny wobble of a star caused by the gravitational pull of an orbiting planet. This wobble reveals the planet's mass. Combining these two techniques allows scientists to calculate the planet's density, which helps determine whether it's primarily rocky, gaseous, or something in between. But even with these methods, much about these planets remains a mystery. For example, scientists have found planets with densities that make no sense based on our current understanding of planetary formation. Some super-Earths are so dense that they could be composed almost entirely of iron, while others are so low in density they might be covered in thick layers of gas or water. These oddball planets challenge our models and push us to refine our theories. The atmospheres of these planets are another puzzle. On Earth, the atmosphere is a delicate balance of gases like nitrogen and oxygen, with trace amounts of carbon dioxide and water vapor. But on super-Earths and mini-Neptunes, atmospheres might be dominated by hydrogen, helium, or even exotic substances we've never encountered before. The temperatures on these worlds can vary wildly, depending on their distance from their parent star. Some might have scorching atmospheres hotter than the surface of Venus, while others could be frigid, with temperatures hundreds of degrees below freezing. Interestingly, some super-Earths orbit very close to their stars, completing a full orbit in just a few days. These are known as hot super-Earths, and they face extreme conditions. Their atmospheres can be stripped away by the intense radiation from their star, leaving behind a bare rocky core. This process, known as atmospheric escape, helps scientists understand how planets lose their atmospheres over time. Meanwhile, mini-Neptunes that orbit farther from their stars might retain their thick gaseous envelopes, creating conditions that are stable over billions of years. If such a planet had the right mix of temperature, pressure, and chemical composition, it could theoretically support life, not on its surface, but perhaps in its atmosphere. This possibility has sparked discussions about aerial life forms that could float in the dense atmospheres of such planets, similar to how certain microbes float in Earth's atmosphere. The potential for life on these worlds is one of the most exciting aspects of their study. While Earth-like planets in the so-called habitable zone tend to dominate the headlines, super-Earths and mini-Neptunes could also host life, albeit under very different conditions. For instance, a water-rich super-Earth might have oceans hundreds of kilometers deep. Beneath these oceans, the immense pressure could create exotic forms of ice that act as a barrier, separating the water from the planet's rocky core. This setup might seem inhospitable, but even here, life could exist, feeding on chemical energy from hydrothermal vents. The discovery of super-Earths and mini-Neptunes has also forced scientists to rethink what makes a planet habitable. On Earth, life thrives in a narrow range of conditions: temperatures where water remains liquid, an atmosphere rich in oxygen, and a magnetic field that protects us from harmful solar radiation. But life on other planets might not play by the same rules. It's possible that alien life could adapt to extreme heat, crushing pressure, or even toxic atmospheres. In fact, some scientists argue that super-Earths might be more habitable than Earth, offering stable environments where life could persist for billions of years. What makes this even more fascinating is how common these planets are. In our galaxy alone, there are an estimated 100 billion planets, and super-Earths and mini-Neptunes make up the majority of them. This means that the conditions for life, or at least the raw materials for it, might be far more widespread than we ever imagined. If life can arise on one of these worlds, it might not be a rare cosmic accident but rather a common outcome of planetary evolution. To understand these planets better, scientists are turning to cutting-edge technology. The James Webb Space Telescope, for example, is capable of analyzing the atmospheres of distant exoplanets in unprecedented detail. By studying the light from stars that passes through a planet's atmosphere, Webb can identify the chemical fingerprints of different molecules. This could reveal whether a planet's atmosphere contains water, oxygen, or even signs of biological activity. Closer to home, missions like TESS, the Transiting Exoplanet Survey Satellite, and Cheops, the Characterizing Exoplanet Satellite, are discovering new super-Earths and mini-Neptunes at an astonishing rate. Each new discovery adds a piece to the puzzle, helping us understand how these planets form, evolve, and interact with their parent stars. As we continue to study these strange new worlds, one thing becomes clear: the universe is far more diverse and complex than we ever imagined. Super-Earths and mini-Neptunes are just the beginning. They hint at a cosmos filled with endless possibilities, where the rules of planet formation and habitability are constantly being rewritten. The sheer diversity of super-Earths and mini-Neptunes opens up profound questions about how planets form in the first place. In our solar system, we see a relatively clear divide between terrestrial planets, like Earth and Mars, and gas giants, like Jupiter and Saturn. However, the existence of planets that sit between these categories, larger than Earth but smaller than Neptune, suggests that the processes of planetary formation might be far more flexible than previously thought. To understand this, scientists rely on a framework called the core accretion model. This model proposes that planets begin as small clumps of dust and gas in a protoplanetary disk, the swirling material around a young star. Over time, these clumps grow larger through collisions and accretion, eventually forming planetesimals, the building blocks of planets. If a planetesimal grows large enough, it can begin to attract a significant atmosphere of hydrogen and helium, eventually becoming a gas giant. But here's where super-Earths and mini-Neptunes throw a wrench into the model. These planets seem to occupy a strange middle ground where they've accumulated more mass than terrestrial planets, but haven't quite grown into full-fledged gas giants. Why do some planets stop growing at this stage? Is there a cutoff point in the amount of material available in the protoplanetary disk? Or do other factors, like the planet's distance from its star or the timing of its formation, play a more significant role? One idea is that super-Earths and mini-Neptunes form in regions of the disk where there's just enough material to allow for moderate growth but not enough to create a gas giant. These planets might represent an intermediate step in the planetary formation process, worlds that could have become gas giants if given more time or resources. Alternatively, some scientists suggest that these planets might have started as gas giants, but lost much of their atmospheres due to the intense radiation from their parent stars. The loss of atmospheres is particularly intriguing. In our solar system, the atmospheres of planets like Earth and Mars have evolved significantly over billions of years. But on close-in super-Earths and mini-Neptunes, this process could be accelerated by their proximity to their stars. These planets are often subjected to extreme levels of ultraviolet radiation, which can strip away lighter gases like hydrogen and helium. What's left behind is a planet with a denser, thinner atmosphere, or, in some cases, no atmosphere at all. This brings us to a fascinating question: what happens to a mini-Neptune that loses its atmosphere? Some scientists believe that these stripped planets could transform into what we call supermercuries, dense, rocky worlds with metallic cores and little to no atmosphere. If this hypothesis is correct, it would mean that many of the rocky exoplanets we've discovered might actually be the remnants of once larger worlds. Another key factor in the formation of these planets is their location within the protoplanetary disk. The so-called snow line is a critical boundary in this disk, marking the region where temperatures are low enough for volatile compounds like water and methane to condense into solid ice. Beyond the snow line, there's generally more material available for planet formation, leading to the creation of larger planets. Super-Earths and mini-Neptunes that form beyond this line might be rich in water and other volatiles, giving them entirely different compositions from their counterparts closer to the star. Interestingly, some mini-Neptunes might migrate inward after forming beyond the snow line. This migration process could bring them into their star's habitable zone, where conditions might allow for liquid water to exist on their surfaces, or, more likely, beneath thick layers of ice or gas. These migrated mini-Neptunes are particularly intriguing because they could harbor subsurface oceans, environments that scientists consider some of the most promising for life. Subsurface oceans are a hot topic in the search for extraterrestrial life. In our solar system, moons like Europa and Enceladus are thought to have liquid oceans beneath their icy crusts, warmed by the gravitational interactions with their parent planets. A similar mechanism could operate on mini-Neptunes, where internal heating from radioactive decay or tidal forces might maintain liquid water beneath thick layers of ice. If these oceans exist, they could provide stable, long-lived environments where life might evolve. The potential for life on super-Earths and mini-Neptunes also depends on their atmospheres. For a planet to support life as we know it, its atmosphere needs to strike a delicate balance. It must be thick enough to trap heat and maintain liquid water, but not so thick that it creates a runaway greenhouse effect. This balance is influenced by factors like the planet's mass, its distance from its star, and the chemical composition of its atmosphere. One of the most exciting discoveries in recent years is the detection of water vapor in the atmospheres of some super-Earths and mini-Neptunes. Water is a key ingredient for life, and its presence suggests that these planets might have the right conditions for habitability. However, the presence of water doesn't guarantee that a planet is hospitable. Other factors, like high levels of radiation or a lack of essential nutrients, could make these worlds inhospitable to life as we know it. Despite these challenges, the discovery of water vapor has fueled speculation about what kinds of life might exist on these planets. Could there be simple microorganisms floating in the upper atmospheres of mini-Neptunes? Could subsurface oceans on water-rich super-Earths harbor complex ecosystems? These questions remain unanswered, but they highlight the tantalizing possibilities that these planets represent. As we continue to study these worlds, we're also learning more about their role in the broader context of planetary systems. Super-Earths and mini-Neptunes often appear in systems with multiple planets, suggesting that their formation is tied to the dynamics of their entire system. For instance, the gravitational interactions between planets can influence their orbits, leading to phenomena like orbital resonances or even planetary collisions. These interactions could explain some of the unusual densities and compositions we see in these planets. Moreover, the presence of super-Earths and mini-Neptunes in a system can influence the habitability of other planets. For example, a large mini-Neptune with a thick atmosphere could act as a shield, deflecting harmful asteroids and comets away from smaller, potentially habitable planets in the same system. Alternatively, the gravitational influence of a super-Earth could destabilize the orbits of nearby planets, making their conditions less hospitable. The study of these planets is still in its early stages, but the discoveries we've made so far are already reshaping our understanding of the universe. Each new super-Earth and mini-Neptune we discover adds another piece to the puzzle, helping us answer fundamental questions about how planets form, evolve, and support life. And yet, for every question we answer, new ones emerge. What are the interiors of these planets like? Could they host forms of life that are completely alien to us? How common are habitable conditions in the galaxy? These mysteries are what make the study of super-Earths and mini-Neptunes so exciting. They remind us that the universe is vast, complex, and full of surprises. The interiors of super-Earths and mini-Neptunes present one of the most intriguing challenges in planetary science. Understanding what lies beneath their surfaces, or even if they have solid surfaces, is crucial for piecing together the full picture of these mysterious worlds. Unlike Earth, whose crust we can study directly, the conditions on these distant planets make direct observation impossible. Instead, scientists rely on theoretical models, indirect measurements, and comparisons with our solar system's planets to infer what these interiors might look like. One critical factor is the planet's density. By measuring the mass and radius of a super-Earth or mini-Neptune, scientists can calculate its average density, which provides clues about its composition. A high-density planet might consist largely of rock and metal, similar to Earth or Mercury. On the other hand, a low-density planet might have a thick atmosphere or be rich in volatile compounds like water, ammonia, or methane. Some super-Earths are thought to have iron-rich cores surrounded by layers of silicate rock, much like Earth. However, their greater mass means they would have much stronger gravitational forces, leading to extreme pressures and temperatures deep within their interiors. These conditions could produce exotic materials, such as superionic water, a phase of water that behaves like both a solid and a liquid under high pressure. This strange substance could play a key role in the geological processes of these planets, including the formation of magnetic fields. Magnetic fields are another intriguing aspect of these worlds. On Earth, the magnetic field is generated by the movement of molten iron in the planet's core, a process known as the dynamo effect. If super-Earths have similar cores, they might also generate magnetic fields, which could protect their atmospheres from being stripped away by stellar winds. This protection could be crucial for maintaining conditions suitable for life. However, the strength and stability of these magnetic fields would depend on factors like the planet's rotation rate and internal composition, both of which vary widely among exoplanets. Mini-Neptunes, with their thick atmospheres and lower densities, present a different set of mysteries. Their interiors are likely dominated by high-pressure layers of hydrogen, helium, and other volatile substances. Beneath these gaseous layers, there might be a dense, ice, layer composed of water, ammonia, and methane, existing in exotic forms due to the intense pressures and temperatures. Deeper still, these planets might have rocky or metallic cores, but the exact composition and structure of these cores remain unknown. The transition between the gaseous atmosphere and the solid or liquid interior is another area of active research. On Earth, the atmosphere is relatively thin compared to the planet's size, but on mini-Neptunes, the atmosphere could account for a significant fraction of the planet's volume. The boundary between the atmosphere and the interior might not be as clearly defined as it is on Earth. Instead, there could be a gradual transition, with the gas becoming denser and hotter until it behaves more like a liquid. These extreme conditions make it difficult to predict what kinds of geological or atmospheric processes might occur on mini-Neptunes. For example, on Earth, the movement of tectonic plates shapes the planet's surface and plays a crucial role in the carbon cycle, which regulates the climate. But on a mini-Neptune, with its thick atmosphere and possible lack of a solid surface, these processes might look entirely different, or might not occur at all. The atmospheres of super-Earths and mini-Neptunes are also key to understanding their potential habitability. Many of these planets are located close to their stars, where intense radiation can strip away lighter elements like hydrogen and helium. However, some planets seem to retain thick atmospheres despite their proximity to their stars. This raises questions about how these atmospheres form and evolve. One possibility is that these planets form farther from their stars, where conditions are cooler and more conducive to retaining thick atmospheres, and then migrate inward. This process of planetary migration could explain why we see so many mini-Neptunes in close orbits around their stars, a configuration that doesn't exist in our solar system. However, migration is a complex process that can disrupt the orbits of other planets in the system, leading to chaotic gravitational interactions. Another possibility is that these planets have mechanisms for replenishing their atmospheres, such as outgassing from their interiors. On Earth, volcanic activity releases gases like carbon dioxide and water vapor into the atmosphere, and similar processes could occur on super-Earths. However, the extreme pressures and temperatures on these planets could produce entirely different gases, creating atmospheres that are unlike anything we see in our solar system. The chemical composition of these atmospheres is a major focus of exoplanet research. Using telescopes like the Hubble Space Telescope and the James Webb Space Telescope, scientists can analyze the light that passes through a planet's atmosphere as it transits its star. This technique, known as transmission spectroscopy, allows researchers to identify the signatures of different molecules, such as water vapor, methane, carbon dioxide, and even complex organic compounds. The discovery of water vapor in the atmospheres of some super-Earths and mini-Neptunes has been particularly exciting. Water is a fundamental ingredient for life as we know it, and its presence suggests that these planets might have the right conditions for habitability. However, water vapor alone is not enough to determine whether a planet is habitable. Factors like temperature, pressure, and the presence of other chemicals also play a crucial role. For example, a planet with a thick atmosphere of water vapor might experience a runaway greenhouse effect, where the atmosphere traps so much heat that the surface becomes too hot for liquid water to exist. This is thought to have happened on Venus, which has a thick atmosphere of carbon dioxide and surface temperatures hot enough to melt lead. On the other hand, a planet with a thinner atmosphere might lose its water to space, leaving behind a dry, barren world. The potential for life on these planets also depends on the stability of their atmospheres. Planets that are too close to their stars might experience extreme temperature fluctuations or intense radiation, which could strip away their atmospheres or prevent complex molecules from forming. Conversely, planets that are too far from their stars might have atmospheres that are too cold or too thick to support life. Despite these challenges, the study of super-Earths and mini-Neptunes has opened up new possibilities for finding life beyond our solar system. These planets represent a vast, untapped reservoir of potential habitats, each with its own unique conditions and challenges. As our technology improves and we discover more about these worlds, we're likely to find even more surprises that challenge our understanding of what makes a planet habitable. In many ways, super-Earths and mini-Neptunes are a reminder of how little we know about the universe. Each new discovery adds another layer of complexity to the puzzle, forcing us to rethink our assumptions and expand our horizons. These planets may not fit neatly into the categories we've developed based on our solar system, but that's exactly what makes them so fascinating. The study of these strange new worlds is still in its infancy, but it's already transforming our understanding of planetary science. As we continue to explore the universe, super-Earths and mini-Neptunes will undoubtedly play a central role in the search for life and the quest to understand our place in the cosmos. The question of habitability on super-Earths and mini-Neptunes often leads scientists to examine the concept of the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. While this concept works well for Earth-like planets, it becomes more complicated for super-Earths and mini-Neptunes due to their diverse compositions and atmospheric characteristics. For example, some of these planets may retain heat through thick atmospheres or generate internal heat via gravitational interactions with their host stars or neighboring planets, potentially allowing liquid water to exist even outside the traditional habitable zone. These possibilities expand the range of environments where life could potentially arise. On Earth, life is found in extreme conditions, from hydrothermal vents on the ocean floor to frozen tundras. This resilience suggests that life might be equally adaptable on other planets, perhaps thriving beneath thick atmospheres or in subsurface oceans shielded from harmful radiation. However, the chemical building blocks of life, carbon, hydrogen, oxygen, nitrogen, and phosphorus, must still be present, along with energy sources to drive biological processes. Energy sources are a critical factor for life on super-Earths and mini-Neptunes. While Earth relies primarily on sunlight for energy, planets with thick atmospheres or distant orbits might depend on other sources, such as geothermal heat or tidal forces. Tidal heating, caused by gravitational interactions between a planet and its star or moons, can generate substantial energy. In our solar system, this phenomenon powers subsurface oceans on icy moons like Europa and Enceladus, and it could play a similar role on distant exoplanets. The search for biosignatures, chemical markers of life, in the atmospheres of these planets is a major goal of modern astronomy. Potential biosignatures include oxygen, methane, and ozone, which can be produced by biological processes. However, these gases can also be generated through non-biological means, such as volcanic activity or chemical reactions in the atmosphere. Distinguishing between biological and non-biological sources requires a comprehensive understanding of a planet's environment, including its temperature, pressure, and chemical composition. The study of super-Earths and mini-Neptunes has also prompted scientists to reconsider the definitions of life and habitability. On Earth, life is carbon-based and depends on water as a solvent. But in the vast diversity of the universe, life might take forms that are entirely unfamiliar to us. Some scientists speculate about the possibility of silicon-based life or organisms that use solvents other than water, such as methane or ammonia. These hypothetical forms of life could thrive in environments that would be hostile to Earth-based organisms, such as the high-pressure atmospheres of mini-Neptunes. This broader perspective is essential for interpreting the data collected by telescopes and space missions. For example, a thick atmosphere dominated by methane and ammonia might seem inhospitable based on our Earth-centric understanding of life. However, it could potentially harbor exotic forms of life that are adapted to these conditions. Similarly, a planet with high surface temperatures and no liquid water might still have subsurface environments where life could exist. The role of planetary formation in shaping the characteristics of super-Earths and mini-Neptunes is another area of intense research. These planets are thought to form in the protoplanetary disks of gas and dust that surround young stars. The composition of a planet depends on the materials available in the disk, as well as the planet's distance from its star. Closer to the star, high temperatures cause volatile compounds like water and methane to evaporate, leaving behind rocky materials. Farther from the star, cooler temperatures allow volatile compounds to condense, leading to the formation of gas giants and ice-rich planets. Super-Earths and mini-Neptunes occupy an intermediate position in this spectrum, and their formation mechanisms are not fully understood. One hypothesis is that they form like smaller versions of gas giants, accreting thick atmospheres of hydrogen and helium around rocky or icy cores. Another possibility is that they form as large terrestrial planets, with atmospheres generated by outgassing from their interiors or captured from the surrounding disk. The relative importance of these processes likely varies from planet to planet, depending on factors like the mass of the protoplanetary disk and the planet's location within it. The diversity of super-Earths and mini-Neptunes suggests that multiple formation pathways are possible. Some of these planets may have started as gas giants that lost their outer layers due to intense radiation from their stars, leaving behind their dense cores. Others might represent failed gas giants that never accumulated enough material to become full-fledged giants. The existence of these planets in a wide range of environments, close to their stars, in the habitable zone, or even farther out, supports the idea that planetary formation is a highly dynamic and complex process. The discovery of these planets has also challenged traditional models of planetary systems. In our solar system, there is a clear distinction between terrestrial planets and gas giants, with no intermediate types. The prevalence of super-Earths and mini-Neptunes in other systems suggests that this dichotomy is not universal. Instead, these planets might represent a more common outcome of planetary formation, with our solar system being the exception rather than the rule. As researchers continue to study these worlds, new questions and possibilities arise. For example, some super-Earths and mini-Neptunes might have moons, which could themselves be potential habitats for life. In our solar system, moons like Europa and Titan are among the most promising locations for finding life, and similar moons could exist around exoplanets. Detecting these moons is challenging, but advances in telescope technology and observational techniques could make it possible in the future. Another exciting prospect is the direct imaging of super-Earths and mini-Neptunes. Current methods of detecting exoplanets, such as the transit and radial velocity techniques, provide limited information about their appearances. Direct imaging would allow scientists to study the colors, weather patterns, and surface features of these planets, offering unprecedented insights into their nature. While this level of detail is still beyond our reach, upcoming missions like the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope could bring us closer to this goal. The study of super-Earths and mini-Neptunes is a testament to the rapid progress of modern astronomy. Just a few decades ago, the existence of planets beyond our solar system was purely theoretical. Today, we have identified thousands of exoplanets, each with its own unique characteristics and mysteries. Among them, super-Earths and mini-Neptunes stand out as particularly fascinating objects of study, offering a glimpse into the diversity of planetary systems and the potential for life beyond Earth. These planets remind us of the vastness and complexity of the universe. They challenge our assumptions, broaden our horizons, and inspire us to keep exploring. As we continue to unravel their secrets, we move closer to answering some of humanity's most profound questions. Are we alone in the universe? What other forms of life and environments might exist? And how do these distant worlds fit into the grand tapestry of the cosmos? The exploration of super-Earths and mini-Neptunes offers a unique perspective on how planets might evolve differently depending on their initial conditions and environments. One of the intriguing mysteries is how their atmospheres develop and change over time. The atmospheric composition of these planets can be influenced by several factors, including their proximity to the host star, their mass, and their initial chemical makeup. For example, a mini-Neptune that forms close to its star might experience significant atmospheric loss due to stellar radiation, gradually transforming into a super-Earth with a thinner atmosphere. This process, known as photoevaporation, occurs when high-energy radiation from the star strips away the lighter elements in a planet's atmosphere. Over millions or billions of years, this can dramatically alter a planet's size, density, and surface conditions. Observations of exoplanets in various stages of atmospheric loss provide valuable insights into this phenomenon. In some cases, we might be witnessing planets in transition, objects that started as mini-Neptunes but are now evolving into rocky super-Earths due to prolonged exposure to intense stellar radiation. The concept of atmospheric stripping also raises questions about the potential for habitability. A planet that loses most of its atmosphere might end up with surface conditions similar to those on Earth, particularly if it retains enough water or other volatile compounds. On the other hand, excessive atmospheric loss could leave a barren, lifeless world with little to no protection from cosmic radiation or the heat of its star. Understanding the balance between these outcomes is crucial for assessing the habitability of super-Earths and mini-Neptunes. Another fascinating area of study is the potential for secondary atmospheres, atmospheres that form after the initial atmosphere has been lost. These secondary atmospheres can arise from volcanic outgassing, impacts with comets or asteroids, or interactions with a planet's surface or interior. On Earth, volcanic activity plays a significant role in replenishing the atmosphere with gases like carbon dioxide, water vapor, and sulfur compounds. Similar processes could occur on super-Earths, potentially creating atmospheres that are conducive to life. However, the composition and thickness of a secondary atmosphere depend on the planet's geological activity, internal heat, and surface composition. A highly active planet with abundant volcanic activity might develop a dense, carbon-rich atmosphere, while a geologically dormant planet might struggle to sustain any atmosphere at all. These variations add another layer of complexity to the study of exoplanets, highlighting the need for detailed observations and advanced models to understand their unique characteristics. One of the most compelling aspects of super-Earths and mini-Neptunes is their potential to host exotic climates and weather systems. On Earth, weather is driven by the interaction of sunlight with the atmosphere, creating phenomena like rain, wind, and hurricanes. On a super-Earth or mini-Neptune, the presence of a thicker atmosphere or different chemical composition could result in entirely unfamiliar weather patterns. For instance, a planet with a hydrogen-rich atmosphere might experience storms of ammonia or methane, while a planet with high surface pressures might have constant, planet-wide winds. These weather systems could have profound implications for the planet's habitability and overall environment. A stable, moderate climate might support the development of life, while extreme conditions, such as superheated storms or perpetual cloud cover, could make the surface inhospitable. Understanding these dynamics requires not only observations of the planet's atmosphere but also sophisticated climate models that can simulate the complex interactions between a planet's surface, atmosphere, and star. The study of these planets also intersects with the search for technological or artificial signatures, evidence of advanced civilizations that might inhabit them. While the primary focus of exoplanet research is on natural processes, some scientists are exploring the possibility that certain atmospheric or surface features could indicate technological activity. For example, unusual chemical imbalances in a planet's atmosphere or consistent patterns of energy emissions could be interpreted as potential signs of artificial influence. Though speculative, this line of inquiry adds an exciting dimension to the search for life beyond Earth. The diversity of super-Earths and mini-Neptunes also raises intriguing questions about the architecture of planetary systems. Unlike our solar system, which has a relatively orderly arrangement of planets, many exoplanetary systems feature planets with wildly varying sizes, compositions, and orbits. The presence of super-Earths and mini-Neptunes in these systems suggests that planetary formation is a highly chaotic and dynamic process, influenced by factors such as the migration of planets, gravitational interactions, and the distribution of materials in the protoplanetary disk. Planetary migration, in particular, is thought to play a significant role in shaping these systems. As young planets interact with the gas and dust in their surrounding disks, they can move inward or outward from their original orbits. This process can bring super-Earths and mini-Neptunes closer to their stars, where they might undergo atmospheric loss, or push them farther out, where they might retain their thick atmospheres. The result is a diverse range of planets with unique histories and characteristics, each providing a piece of the puzzle in our understanding of planetary formation. Another exciting development is the use of advanced telescopes to study the atmospheres of super-Earths and mini-Neptunes in greater detail. Instruments like the James Webb Space Telescope, JWST, and ground-based observatories equipped with adaptive optics are enabling scientists to detect and analyze the chemical composition of these planets' atmospheres. By observing how starlight interacts with a planet's atmosphere, researchers can identify the presence of gases like water vapor, carbon dioxide, and methane, which provide clues about the planet's environment and potential habitability. These observations are not without challenges. The vast distances to these planets, combined with the faintness of their host stars, make it difficult to obtain high-resolution data. Moreover, the interpretation of atmospheric spectra requires careful consideration of factors like clouds, haze, and temperature variations, which can obscure or mimic the signatures of certain gases. Despite these difficulties, the progress made in recent years is a testament to the ingenuity and determination of scientists working in this field. Looking ahead, the future of exoplanet research holds immense promise. Upcoming missions like the European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, and NASA's Habitable Worlds Observatory are poised to revolutionize our understanding of super-Earths and mini-Neptunes. These missions aim to survey the atmospheres of hundreds of exoplanets, providing a wealth of data that will help answer fundamental questions about their nature, origins, and potential for life. The study of these planets is not just an academic exercise, it has profound implications for humanity's place in the universe. By exploring the diversity of worlds beyond our solar system, we gain a deeper appreciation for the complexity and beauty of the cosmos. At the same time, we confront the possibility that life might exist in forms and environments far beyond our imagination. These discoveries challenge us to rethink our assumptions, expand our horizons, and continue the quest to understand our universe and our role within it. The journey to uncover the mysteries of super-Earths and mini-Neptunes is as much about refining our technological capabilities as it is about expanding our scientific knowledge. One of the most transformative advancements in this field has been the development of precision measurement techniques, particularly those used in detecting and characterizing exoplanets. Instruments like spectrographs and photometers, combined with sophisticated algorithms, allow scientists to detect minute changes in starlight caused by orbiting planets. These changes, known as transit events or radial velocity shifts, provide critical data about a planet's size, mass, and orbital distance. For super-Earths and mini-Neptunes, such measurements often reveal unexpected results. For example, some super-Earths are incredibly dense, suggesting a rocky composition similar to Earth's, while others have densities so low that they appear to be mostly gas. This variability hints at a broad spectrum of planetary formation processes. Mini-Neptunes, on the other hand, tend to have thick hydrogen-helium atmospheres, making them less dense overall but still fascinating in terms of their potential to harbor exotic cloud formations or weather systems. Another intriguing aspect of studying these planets is understanding their interiors. Unlike terrestrial planets like Earth, where seismic activity can provide clues about internal structure, the interiors of exoplanets remain largely speculative. Scientists rely on models of planetary formation and evolution to infer the composition of these worlds. For instance, a dense super-Earth might have a large iron core surrounded by silicate rock, while a less dense mini-Neptune might contain significant amounts of water, ice, or even exotic materials like supercritical fluids. The concept of water worlds is particularly exciting when discussing mini-Neptunes. These planets may have thick layers of water and other volatiles beneath their atmospheres, potentially forming deep oceans or icy mantles. The high pressures and temperatures in such environments could lead to the formation of exotic states of water, such as I-7 or superionic water, which behave differently from the water we know on Earth. These conditions might even support life in forms vastly different from what we're familiar with, raising the possibility of biospheres hidden beneath thick clouds or layers of ice. Astrobiology, the study of life in the universe, has naturally turned its attention to super-Earths and mini-Neptunes. The sheer number of these planets in the galaxy increases the likelihood of finding habitable environments. However, determining habitability requires careful consideration of many factors. For instance, the planet's distance from its star plays a crucial role in determining surface temperatures and the presence of liquid water. This region, known as the habitable zone or Goldilocks zone, is where conditions are just right for water to exist in liquid form, a key ingredient for life as we know it. Interestingly, some super-Earths and mini-Neptunes exist within the habitable zones of their stars, making them prime candidates for further study. But habitability isn't solely about location. The composition of a planet's atmosphere, its magnetic field, and even its geological activity can all influence whether it could support life. A thick atmosphere rich in greenhouse gases might keep a planet warm enough for liquid water, while a strong magnetic field could shield it from harmful cosmic radiation. These factors make the search for habitable exoplanets a complex but incredibly rewarding endeavor. Super-Earths and mini-Neptunes also challenge our understanding of the rare Earth hypothesis, which suggests that Earth-like conditions might be extraordinarily uncommon in the universe. The discovery of so many planets in this size range indicates that Earth-like worlds could be more abundant than previously thought. However, these planets differ significantly from Earth in terms of composition, atmosphere, and potential habitability. Understanding these differences helps refine our models of planetary formation and the likelihood of finding truly Earth-like worlds elsewhere in the galaxy. The diversity of super-Earths and mini-Neptunes also provides valuable context for understanding the uniqueness, or lack thereof, of our own solar system. In many ways, our solar system appears to be an outlier. It lacks planets in the size range between Earth and Neptune, and its arrangement of terrestrial planets near the Sun and gas giants farther out is relatively uncommon among the systems we've observed. This raises questions about why our solar system formed the way it did, and whether its configuration played a crucial role in the development of life on Earth. Some scientists propose that the absence of super-Earths or mini-Neptunes in our solar system might have been a stroke of luck. A larger planet in the inner solar system could have disrupted the orbits of smaller terrestrial planets, potentially preventing the formation of Earth or destabilizing its climate. Alternatively, the presence of a mini-Neptune might have altered the distribution of volatiles, such as water, making Earth less hospitable to life. These hypotheses highlight the delicate balance of factors that can influence the evolution of planetary systems and their potential for supporting life. The exploration of super-Earths and mini-Neptunes is also driving innovation in space exploration technology. Missions like the Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope, JWST, are specifically designed to study exoplanets in unprecedented detail. TESS, for example, focuses on identifying planets around bright, nearby stars, making them easier to study with follow-up observations. JWST, with its powerful infrared capabilities, can analyze the atmospheres of these planets, searching for signs of water vapor, methane, carbon dioxide, and other molecules that might indicate habitability. Future missions, such as the European Space Agency's Plato, planetary transits and oscillations of stars, aim to expand our understanding even further. Plato will focus on characterizing Earth-sized and super-Earth-sized planets in the habitable zones of their stars, providing crucial data on their potential for hosting life. These missions represent a new era in planetary science, where the focus shifts from merely discovering planets to understanding their nature and potential for habitability. In addition to space-based observatories, ground-based telescopes are playing a critical role in studying super-Earths and mini-Neptunes. Advanced instruments like the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, are being designed to capture high-resolution images and spectra of exoplanets, providing complementary data to space-based missions. These facilities will enable scientists to study planets in greater detail, from their atmospheric composition to their surface conditions. Ultimately, the study of super-Earths and mini-Neptunes is a testament to humanity's insatiable curiosity and drive to explore the unknown. Each new discovery challenges our understanding of the universe and inspires us to ask deeper questions about our place within it. These strange new worlds, with their diverse characteristics and potential for life, remind us that the cosmos is far more complex and wondrous than we could ever imagine. As we continue to explore and learn, we inch closer to answering some of the most profound questions of existence. Are we alone? What other worlds are out there? And what can they teach us about the nature of reality itself? The quest to understand super-Earths and mini-Neptunes doesn't just expand our knowledge of exoplanets. It reshapes our understanding of planetary formation as a whole. Traditionally, planetary formation theories were largely modeled on the architecture of our own solar system. Gas giants were expected to form in the colder, outer regions where icy materials could accumulate, while rocky planets like Earth and Venus formed closer to the Sun, where temperatures were too high for gases to condense. However, the sheer diversity of exoplanetary systems has shattered this simplistic model. Super-Earths and mini-Neptunes defy these expectations in numerous ways. Many of them exist in orbits much closer to their parent stars than any planet in our solar system, often completing a revolution in just a few days. These hot exoplanets experience extreme radiation and heat, which likely alters their atmospheric compositions and internal structures. This raises questions about how such planets formed in the first place. Did they form in these close orbits, or did they migrate inward from farther out in their planetary systems? The migration hypothesis is one of the leading theories to explain the unusual positions of these planets. According to this model, planets often form in the colder, outer regions of a protoplanetary disk, where materials like ice and gas are more abundant. Over time, gravitational interactions with the disk or other planets can cause these worlds to spiral inward, settling into close orbits. This process of migration could help explain why mini-Neptunes, which are thought to have thick, volatile-rich atmospheres, are found so close to their stars. However, migration is not without its complications. As planets move inward, they interact with the material in the protoplanetary disk, which can create turbulent forces that either slow down or speed up their motion. This can lead to chaotic systems where planets are flung into eccentric orbits, or even ejected entirely from their systems. Despite these challenges, many super-Earths and mini-Neptunes seem to occupy stable orbits, suggesting that the migration process, if it occurred, was more orderly than chaotic. Another puzzling aspect of these planets is their atmospheres. Mini-Neptunes, in particular, have thick envelopes of hydrogen and helium, which are usually associated with much larger gas giants like Jupiter and Saturn. How did these smaller planets manage to retain such massive atmospheres? One possibility is that they formed early in the life of their planetary systems, when the protoplanetary disk was still rich in gas. By rapidly accreting gas from the disk, these planets could have developed their thick atmospheres before the disk dispersed. On the other hand, the atmospheres of some super-Earths appear to have been stripped away entirely, leaving behind bare rocky cores. This could be the result of their close proximity to their stars, where intense stellar radiation and winds can erode an atmosphere over time. The existence of such stripped planets adds yet another layer of complexity to our understanding of these worlds. It also highlights the importance of studying planetary atmospheres to gain insights into their evolutionary histories. Advancements in spectroscopy have been instrumental in unraveling the mysteries of these atmospheres. By analyzing the light that passes through or reflects off a planet's atmosphere, scientists can identify the chemical compounds present. For example, the detection of water vapor in a mini-Neptune's atmosphere might suggest a volatile-rich environment, while the presence of carbon dioxide or methane could indicate processes that resemble those on Earth. These observations not only provide clues about the planet's composition but also help us assess its potential for habitability. Habitability remains one of the most compelling questions in the study of super-Earths and mini-Neptunes. While their large sizes and thick atmospheres make them less likely to resemble Earth, some scientists believe that certain conditions could still support life. For instance, a super-Earth with a dense atmosphere could maintain surface temperatures suitable for liquid water, even if it orbits slightly outside its star's traditional habitable zone. Similarly, mini-Neptunes with deep subsurface oceans could harbor life forms adapted to extreme pressures and chemical environments. The possibility of life on these planets challenges our Earth-centric notions of habitability. Life on Earth is largely dependent on sunlight and carbon-based chemistry, but other forms of life might thrive in conditions that seem hostile to us. For example, extremophiles on Earth, organisms that live in environments like deep-sea hydrothermal vents or acidic hot springs, demonstrate that life can adapt to a wide range of conditions. If similar organisms exist on super-Earths or mini-Neptunes, they could provide a glimpse into the diversity of life forms in the universe. To explore these possibilities, future missions will need to go beyond simply detecting exoplanets. Instruments capable of directly imaging these worlds and analyzing their atmospheres in detail will be crucial. Technologies like star shades and coronagraphs, which block out the light of a star to reveal its surrounding planets, could revolutionize our ability to study exoplanets. By obtaining high-resolution spectra, we could identify potential biosignatures, chemical markers that might indicate the presence of life. The study of super-Earths and mini-Neptunes also has profound implications for understanding planetary formation on a cosmic scale. By comparing these planets across different star systems, scientists can identify trends that reveal the underlying processes shaping planetary systems. For instance, the prevalence of super-Earths around certain types of stars might indicate that specific conditions favor their formation. Similarly, the chemical diversity of mini-Neptunes could shed light on how elements and compounds are distributed within protoplanetary disks. These comparative studies are particularly important for placing our own solar system in context. Why does our solar system lack super-Earths and mini-Neptunes, while they seem to be so common elsewhere? Did the early formation of Jupiter and Saturn prevent the accretion of intermediate-sized planets? Or does the absence of these planets reflect a unique set of circumstances that allowed Earth to develop its life-sustaining conditions? Answering these questions requires a deeper understanding of the factors that influence planetary formation and evolution. As we continue to explore these strange new worlds, we are reminded of the vastness and complexity of the universe. Each new discovery brings us closer to answering some of the most profound questions about our existence. How common are Earth-like conditions in the cosmos? What other forms of life might exist? And what do these distant worlds tell us about our own planet's history and future? The journey to understand super-Earths and mini-Neptunes is far from over, but every step brings us closer to unlocking the secrets of the universe. The search for answers about super-Earths and mini-Neptunes isn't just about understanding distant worlds. It's also about redefining what we think is possible in the universe. With each new exoplanet discovered, we are forced to confront our assumptions and expectations. These planets, in their strange diversity and complexity, highlight the vast array of potential outcomes in planetary systems. While Earth remains our best-known example of a habitable planet, super-Earths and mini-Neptunes suggest that there might be countless variations of planetary environments that we have yet to fully comprehend. For example, the idea of habitability has been traditionally tied to certain specific conditions. On Earth, we associate habitability with liquid water, an atmosphere composed mainly of nitrogen and oxygen, and a stable, temperate climate. However, what if other forms of habitability exist that don't fit within these parameters? Some of the exoplanets we've discovered have temperatures or atmospheric conditions that, at first glance, seem inhospitable to life. But could there be forms of life that thrive under extreme pressure, radiation, or temperature? Could there be ecosystems based on alternative chemistries, such as those that don't rely on carbon-based molecules? This idea is known as the life as we don't know it hypothesis, and it opens the door to an entirely new realm of possibilities. For instance, life on a super-Earth with a thick, hydrogen-rich atmosphere might not resemble anything we're familiar with, but it could still thrive in environments with extreme temperatures or pressures. Subsurface oceans on mini-Neptunes could offer an environment where life exists under vast layers of water and gas, with minimal light but rich in minerals and chemical compounds. In some respects, these ideas challenge our understanding of biology itself. What if life doesn't require the same conditions we take for granted? Could organisms survive on planets with constant radiation from their parent stars? Could they adapt to extreme gravity, pressure, or even lack of sunlight? These questions push the boundaries of our scientific thinking and remind us that our knowledge is still just the beginning. To explore these questions, we'll need to rethink our tools for studying exoplanets. Future space missions will have to develop highly advanced technology to probe the atmospheres of these distant worlds. The James Webb Space Telescope, set to launch soon, is one of the most anticipated tools for this job. It will allow astronomers to study the composition of exoplanet atmospheres with unprecedented precision. Webb's ability to detect the chemical makeup of distant atmospheres could allow us to identify potential signs of life, or at least conditions that might support it. But even as we look to the future, we must remember how far we've come. The first exoplanet was discovered only a few decades ago, and in that short time, our understanding of the cosmos has expanded exponentially. Today, we know of thousands of exoplanets, each one a potential candidate for exploration and discovery. As we study super-Earths and mini-Neptunes, we are not just looking for planets that might support life, but also for the fundamental forces that drive the evolution of planetary systems. One of the biggest challenges in understanding these planets is also one of the most intriguing: how to reconcile their diversity. Our solar system contains a relatively small number of planets, each one distinct in its composition and characteristics. By comparison, the sheer variety of exoplanets is mind-boggling. Super-Earths and Mini-Neptunes alone come in a range of sizes, atmospheric compositions, and orbital characteristics. Some have atmospheres rich in hydrogen and helium, while others may have thick clouds of carbon dioxide or methane. Some orbit close to their stars in blistering heat, while others are cooler and potentially more hospitable. Understanding why planets in other solar systems are so varied could offer insights into how our own solar system formed and evolved. Could the early solar system have contained more planets, some of which were pushed out by gravitational interactions or massive collisions? Did Jupiter and Saturn play a crucial role in shaping the arrangement of the planets we see today? Or did the conditions on Earth and its neighboring planets simply emerge from a series of rare, unique circumstances? Ultimately, studying super-Earths and mini-Neptunes isn't just about the planets themselves, it's about us. It's about understanding our place in the universe, the history of our own planet, and the future of human exploration. The questions that arise from studying these distant worlds are the same questions that push us to explore the unknown, to take risks, and to look beyond our current knowledge. Whether it's sending robotic spacecraft to distant moons, developing new telescopes to peer deeper into space, or even one day sending humans to exoplanets, the drive to explore is part of who we are. As our exploration of exoplanets continues to evolve, it's likely that we will find even stranger and more unexpected worlds than we've encountered so far. Perhaps we'll discover planets that defy every expectation, with atmospheres made of exotic compounds, oceans of liquid methane, or landscapes unlike anything on Earth. Or maybe we'll discover planets where life exists in ways we can't even begin to imagine. Whatever we find, it will likely deepen our understanding of what is possible in the universe and challenge us to expand our imaginations even further. So, as we continue to study the mysteries of super-Earths and mini-Neptunes, we are embarking on a journey of discovery that transcends the boundaries of science and touches upon the very essence of exploration itself. These strange new worlds remind us of the infinite possibilities that exist in the cosmos, and they compel us to keep pushing forward, to keep seeking, and to keep wondering about what lies beyond the stars. As we look toward the future, the possibilities seem limitless. The ongoing discovery of exoplanets continues to reveal new worlds that challenge our understanding of planetary formation and the potential for life elsewhere in the universe. Super-Earths and mini-Neptunes are just the beginning of this exciting journey. Every new exoplanet we discover brings with it a unique set of questions and challenges, urging scientists to think outside the box and reconsider the nature of planetary systems. One of the key areas of research in the study of super-Earths and mini-Neptunes is their composition. Unlike the rocky planets of our solar system, such as Earth, Mars, and Venus, these exoplanets fall into a category where their size and composition seem to defy traditional classifications. Super-Earths are larger than Earth but smaller than Neptune, and they can have a variety of compositions, ranging from rocky to gaseous. Mini-Neptunes, on the other hand, are planets that are smaller than Neptune but still possess significant atmospheres, often composed of hydrogen, helium, and other volatile gases. The size of these planets raises interesting questions about their formation. In our solar system, planets like Earth and Mars formed from the accumulation of dust and gas in the protoplanetary disk. However, the formation of super-Earths and mini-Neptunes might be more complex. It's possible that these planets formed similarly to gas giants like Jupiter, accumulating massive amounts of gas before their cores could fully solidify. Alternatively, some may have formed as smaller rocky planets that captured significant amounts of gas over time, evolving into the large, volatile worlds we observe today. This leads to the question of how common these planets are in the universe. Scientists are beginning to think that super-Earths and mini-Neptunes may actually be more common than Earth-like planets. In fact, many of the exoplanets discovered so far fall into this category. This could have profound implications for our understanding of the universe and the potential for finding life beyond our solar system. If these planets are indeed more common, it suggests that the conditions for life may be more widespread than we previously thought, even if those conditions are quite different from what we experience on Earth. Another exciting possibility is that these planets could hold the key to understanding the diversity of planetary systems. Super-Earths and mini-Neptunes are likely to experience different processes during their formation compared to the planets in our solar system. For example, their larger size and composition could lead to unique atmospheric conditions, which might result in entirely different weather patterns, geological processes, and chemical cycles. Understanding these processes could provide important clues about the early stages of planetary formation and how different planetary systems evolve over time. To study these distant worlds, astronomers are relying on an array of advanced technologies and techniques. Telescopes like the Hubble Space Telescope, the Spitzer Space Telescope, and the upcoming James Webb Space Telescope will allow scientists to peer into the atmospheres of these exoplanets and analyze their chemical compositions. By studying the light that passes through or reflects off an exoplanet's atmosphere, astronomers can determine the presence of various gases, such as water vapor, methane, and carbon dioxide. This information could provide crucial insights into the potential habitability of these planets, and the processes that govern their climates and ecosystems. In addition to studying the atmospheres of exoplanets, scientists are also using radial velocity and transit methods to detect these distant worlds. The radial velocity method measures the gravitational influence of a planet on its star, causing the star to wobble slightly. By analyzing this wobble, astronomers can determine the mass and orbit of the exoplanet. The transit method, on the other hand, involves observing the dip in a star's brightness when a planet passes in front of it. This method can reveal information about the size and composition of the planet, as well as its atmosphere. As we continue to gather more data on super-Earths and mini-Neptunes, it is likely that we will begin to see patterns emerge in the types of planets that are most common in different parts of the galaxy. Some planets may be more likely to form in specific types of star systems, or certain conditions may favor the creation of large, gaseous planets. Understanding these patterns could help us better predict the types of planets that are most likely to harbor life, and even guide future missions to these distant worlds. One of the biggest challenges in studying these planets is the vast distances between us and them. Even the nearest exoplanets are located many light years away, making direct exploration difficult, if not impossible, with current technology. However, as our space exploration capabilities improve, we may one day be able to send probes or even crewed missions to explore these worlds up close. In the meantime, we must rely on remote sensing and advanced telescopes to learn as much as we can about these distant worlds. The discovery of super-Earths and mini-Neptunes has also led to the development of new theories about the potential for life beyond Earth. For years, scientists have focused on finding planets in the habitable zone of their stars, the region where liquid water could exist on the surface. However, as we explore more diverse exoplanets, it's becoming clear that life may not be limited to these narrow conditions. Some of the most intriguing exoplanets are not in the traditional habitable zone but may still have the right conditions for life, such as subsurface oceans or extreme forms of chemistry. For example, one of the most exciting discoveries in recent years has been the detection of water vapor in the atmospheres of exoplanets. While these planets may not have oceans or lakes on their surfaces, the presence of water vapor suggests that liquid water could exist in other forms, such as in subsurface oceans beneath thick ice sheets. Some scientists believe that life could exist in these environments, where heat from the planet's interior or from tidal forces could provide the necessary energy for life to thrive. These discoveries open up new possibilities for the search for life beyond Earth. If life can exist in such extreme environments, it raises the question, how far can life adapt to different conditions? Could life exist on planets with high radiation levels, extreme temperatures, or even on planets that are constantly bombarded by asteroids and comets? These are questions that scientists are only beginning to explore, and the answers could have profound implications for our understanding of biology, life, and the universe itself. As we continue to search for answers, the study of super-Earths and mini-Neptunes will remain one of the most exciting areas of astronomical research. These strange new worlds challenge our understanding of planetary formation, habitability, and the potential for life beyond our solar system. Each discovery brings us closer to answering some of the most profound questions humanity has ever asked. Are we alone in the universe? And if not, what other forms of life might exist out there? As technology advances and our understanding of exoplanets deepens, we are bound to uncover even more mysteries about these fascinating worlds. And in the process, we may just find answers to some of the most fundamental questions about our place in the cosmos. As we peer deeper into the cosmos, the mysteries of super-Earths and mini-Neptunes only grow more tantalizing. These planets, often located in star systems far beyond our own, offer us a glimpse into a corner of the universe that is vastly different from our own solar system. Despite their size and uniqueness, we are only beginning to scratch the surface in understanding how these worlds form and evolve. The formation of super-Earths and mini-Neptunes remains one of the most debated topics in planetary science. One theory suggests that these planets could have originated in a manner similar to our own gas giants, such as Jupiter or Saturn. In this model, the planet would start off as a small, icy or rocky body, but as it grew, it would accumulate massive amounts of gas, forming a thick, gaseous atmosphere around a small, dense core. However, the process of forming these large atmospheres in such a short time frame is not yet fully understood, and this is where the research is still evolving. Another hypothesis proposes that super-Earths could form in a manner more akin to the way rocky planets like Earth and Venus came into existence, by the gradual accumulation of solid material. However, unlike Earth, these planets would need to gather enough material to form a larger core, enabling them to capture significant amounts of gas from the surrounding protoplanetary disk. The fact that we observe such a wide variety of exoplanets, ranging from gas giants to terrestrial worlds, points to a diversity of planetary formation mechanisms, each dependent on factors like the mass of the planet, the composition of the star system, and the dynamics of the surrounding environment. Some super-Earths may even have evolved in ways that mimic the formation of a mini-Neptune. In this case, a rocky or icy core might first form, but the planet would not have enough mass to capture large amounts of gas in the early stages. Over time, however, it could experience an influx of gas through interactions with its star or neighboring planets, eventually transitioning into a mini-Neptune-like world. This gradual shift in the planet's composition would make it very different from the more stable planets in our solar system, presenting a dynamic evolution in terms of atmospheric chemistry, geological activity, and even the potential for liquid water. What makes these planets even more fascinating is the diversity of conditions they exhibit. Super-Earths, in particular, come in a variety of shapes and sizes. Some are thought to have thick, dense atmospheres that might be made up of hydrogen and helium, akin to Neptune or Uranus. These atmospheres could be so thick and heavy that the planets themselves might be surrounded by intense pressure, similar to the conditions found on the gas giants of our solar system. On the other hand, some super-Earths are rocky, with surface conditions that are vastly different from our own. The combination of these two extremes, gas-dominated and rocky super-Earths, gives scientists a broader picture of the different ways planets can evolve and adapt to their environments. Mini-Neptunes, smaller cousins to the gas giants, also present a unique set of challenges for astronomers. They typically have a small, rocky core surrounded by a thick layer of gas, which gives them their signature characteristics: a large atmosphere that can consist of hydrogen, helium, and other compounds. These planets might be large enough to retain their gaseous envelopes, but not massive enough to develop the same type of high-pressure core found on Jupiter or Saturn. Mini-Neptunes are often distinguished from true gas giants by their smaller size and lower mass, which makes them intriguing subjects for further study. Interestingly, many of the mini-Neptunes discovered in recent years fall within the size range of 2 to 4 times the size of Earth. This makes them distinctly different from the gas giants in our solar system, which are much larger. The discovery of these mini-Neptunes has forced scientists to rethink how planets form and evolve, as their characteristics challenge many of the assumptions that we once held about planetary systems. The fact that these planets are so common in the universe suggests that the process of planet formation is not as rare or exclusive as we might have once thought. One of the most intriguing aspects of these planets is their potential to host life. While super-Earths and mini-Neptunes are not considered Earth-like in terms of their atmosphere or surface conditions, scientists are now considering the possibility that life could exist on these planets in ways that we cannot yet fully imagine. The study of exoplanets, particularly those in the habitable zone of their star, has traditionally focused on finding planets that resemble Earth in terms of their size, distance from their star, and the presence of liquid water. However, as we begin to explore planets like super-Earths and mini-Neptunes, we are coming to realize that life could thrive in far more diverse environments than we previously thought. For example, some super-Earths are thought to have an internal heat source that could potentially create conditions favorable for life beneath their thick atmospheres. In this scenario, life would not depend on sunlight or surface conditions but rather on the heat generated from the planet's interior or from tidal forces caused by gravitational interactions with its star. This means that even in environments that might seem inhospitable on the surface, life could potentially survive in subsurface oceans or deep within the planet's crust. Mini-Neptunes, too, may have potential for life in ways we hadn't considered before. While their atmospheres are often thick and inhospitable, some scientists believe that life could exist beneath the clouds, in environments where heat from the planet's interior or tidal forces could provide the energy necessary for life to persist. If these planets have subsurface oceans, similar to the icy moons of our own solar system, they could potentially harbor life forms that rely on the chemical energy from the planet's interior rather than solar energy. This opens up the exciting possibility that life could exist in extreme environments, challenging our understanding of what constitutes a habitable world. As we learn more about super-Earths and mini-Neptunes, we are gaining valuable insights into the potential for life beyond our solar system. The search for extraterrestrial life is no longer limited to Earth-like planets. Instead, it is expanding to include a wide range of environments that were once thought to be too extreme for life to thrive. The discovery of these strange, new worlds offers us hope that life may exist in forms we have yet to imagine, and that the universe may be far more diverse than we ever thought possible. The technology and methods used to explore these faraway planets are continually evolving. In the coming years, advancements in telescope technology, including the launch of the James Webb Space Telescope and the continued use of ground-based observatories, will allow us to examine exoplanets in greater detail than ever before. By studying the light that filters through their atmospheres or reflects off their surfaces, scientists will be able to detect the presence of gases like methane, carbon dioxide, and water vapor, which could provide vital clues about the composition and potential habitability of these worlds. As the search for super-Earths and mini-Neptunes continues, new discoveries are likely to provide more pieces to the puzzle of planetary formation and the potential for life in the universe. Every new planet we discover adds a new layer of complexity to our understanding of how planets form, evolve, and potentially harbor life. With each breakthrough, we come closer to answering some of the most profound questions humanity has ever asked. How did our solar system come to be? Are we truly alone in the universe? And what does the discovery of these strange new worlds tell us about the potential for life beyond Earth? In the end, the study of super-Earths and mini-Neptunes is about more than just discovering new planets. It's about expanding our understanding of the universe, challenging our assumptions about what is possible, and opening our minds to the infinite possibilities that lie beyond our own solar system. As we continue to explore the cosmos, one thing is clear: the universe is far more mysterious, diverse, and full of potential than we could ever have imagined. The more we look into the characteristics of super-Earths and mini-Neptunes, the more we realize just how strange and diverse planetary systems can be. These planets blur the lines between what we traditionally think of as rocky planets like Earth and gas giants like Jupiter and Saturn. As a result, they challenge our preconceived notions about planetary formation and the conditions that could support life beyond Earth. To understand these planets more thoroughly, let's dive into some of the unique properties they possess and what they might reveal about the history of our universe. For example, the mass and size of super-Earths vary greatly, which means that the atmospheres and internal structures could be equally varied. Some may have thick atmospheres that trap heat, making the surface temperature much higher than we would expect from a planet in the habitable zone. Others might have lighter, thinner atmospheres, or even atmospheres that are mostly composed of gases we associate with gas giants like Neptune. The differences in these atmospheres make it particularly difficult to categorize super-Earths as habitable or not. Unlike Earth, where life is sustained by the presence of oxygen and liquid water, the surface conditions of these planets might be radically different. The possibility of life on these planets, as we've mentioned before, could exist in forms completely unlike anything we know. This is especially intriguing given that we know life on Earth has thrived in extreme environments, from the depths of the oceans near hydrothermal vents to the frozen, desolate conditions of Antarctica's dry valleys. It's not so far-fetched to imagine that life could also survive in extreme environments on distant super-Earths and mini-Neptunes, provided the right conditions exist beneath the surface or in hidden pockets of their atmospheres. Mini-Neptunes, in particular, might offer some of the most exciting clues about the early stages of planetary evolution. These worlds are not massive enough to become true gas giants like Jupiter, but their thick atmospheres still present a tantalizing puzzle for astronomers. Could these planets be remnants of failed gas giants? Or could they be worlds that simply never had enough material to grow beyond their current state? This question is still unanswered, but as we observe more and more of these planets, the data we collect might eventually provide the breakthrough we need to understand what determines whether a planet becomes a gas giant or remains in the mini-Neptune category. The study of these planets also brings into question the possibility of their moons. Much like how moons in our own solar system can vary drastically, from the frigid, icy moons of Jupiter and Saturn to the large, rocky moons like Earth's own moon, moons around super-Earths and mini-Neptunes could be completely different from anything we are familiar with. For instance, a large super-Earth might have moons that are rich in water, providing a potential habitat for life. Meanwhile, a mini-Neptune, with its thick atmosphere and intense winds, might have moons that are shaped by powerful tidal forces or high levels of volcanic activity. As astronomers observe these distant worlds and their moons, they are starting to realize that the presence of a moon can significantly affect a planet's potential for habitability. A moon can help stabilize the orbit of a planet, regulate its climate, and create the conditions necessary for liquid water to exist. This is why the search for moons around super-Earths and mini-Neptunes is gaining attention in the scientific community. Even if the planet itself is not capable of supporting life, its moon may provide a far more hospitable environment. The atmosphere of a planet also plays a crucial role in its potential to support life. For super-Earths and mini-Neptunes, the study of atmospheric composition is particularly important. While Earth's atmosphere is made up mostly of nitrogen and oxygen, with small amounts of other gases like carbon dioxide and water vapor, the atmospheres of these exoplanets are likely very different. Some could be rich in hydrogen, helium, or other gases, creating an atmosphere that is unlike anything we've ever experienced. Understanding how these atmospheres are created and how they evolve over time will give us critical insights into the broader processes of planetary formation and the dynamics of exoplanetary systems. What's particularly fascinating is the sheer number of super-Earths and mini-Neptunes we have discovered so far. In fact, these types of planets make up a significant portion of the exoplanets cataloged by missions like Kepler and TESS. Some scientists believe that super-Earths and mini-Neptunes could be the most common types of planets in the galaxy. If this is true, it could mean that many star systems, even those relatively close to our own, could have planets that are similar in size to Earth but vastly different in composition and atmosphere. These discoveries suggest that our understanding of what constitutes a habitable planet may need to be redefined. In the hunt for potentially habitable planets, scientists have long focused on finding planets in the so-called Goldilocks zone, or the habitable zone of a star where conditions are just right for liquid water to exist on a planet's surface. However, the discovery of super-Earths and mini-Neptunes is pushing us to reconsider whether the presence of liquid water is the sole criterion for habitability. After all, life on Earth thrives in a wide range of environments, from the ocean floor to the Arctic ice sheets, and some scientists argue that life elsewhere might not need Earth-like conditions to survive. One of the challenges in studying these planets is that they are often located far from Earth, making it difficult to study them in detail. Most of the data we have gathered so far about super-Earths and mini-Neptunes comes from analyzing the light that passes through their atmospheres as they orbit their host stars. This technique, known as transmission spectroscopy, allows scientists to study the composition of a planet's atmosphere, looking for signs of water vapor, carbon dioxide, methane, or other chemicals that might suggest the presence of life. However, this method is still relatively limited, and there is much more we can learn by observing these planets in other ways. In the future, new telescopes like the James Webb Space Telescope, JWST, are expected to provide us with much more detailed information about these distant worlds. With its advanced infrared capabilities, the JWST will be able to look deeper into the atmospheres of super-Earths and mini-Neptunes, potentially detecting gases that might indicate the presence of life or at least the conditions necessary for life to exist. The JWST could also give us a better understanding of the conditions on the surfaces of these planets, revealing details about their climates, geology, and potential for habitability. As we continue to push the boundaries of space exploration, the study of super-Earths and mini-Neptunes will play an increasingly important role in our quest to understand the diversity of planets in the universe. These strange new worlds hold the key to unlocking many of the mysteries of planetary formation and the potential for life beyond Earth. By studying these planets in greater detail, we may be able to answer some of the biggest questions in science. How do planets form? What determines whether a planet becomes a gas giant or a rocky world? And most importantly, are we truly alone in the universe? The search for super-Earths, mini-Neptunes, and other exoplanets is just beginning. As technology continues to advance, so too will our ability to explore these distant worlds and uncover their secrets. The more we learn about these planets, the more we realize how much we still have to discover about the vast and mysterious universe in which we live. As we continue to probe deeper into the study of super-Earths and mini-Neptunes, one of the key areas that have captivated scientists is the understanding of how these planets form. Theories about planetary formation have evolved significantly, especially with the discovery of exoplanets that don't neatly fit into the categories of either rocky planets or gas giants. Super-Earths and mini-Neptunes, with their unique characteristics, provide crucial insights into the processes that govern the birth and development of planetary systems. Planet formation is generally thought to occur in a series of stages, beginning with the accumulation of gas and dust in a protoplanetary disk surrounding a young star. In the early stages of this process, dust grains collide and stick together, forming planetesimals. These planetesimals then collide and merge to form planetary embryos, which grow larger over time. For rocky planets like Earth, this process continues until the planet reaches a size where it can gravitationally attract and retain an atmosphere, generally made up of lighter gases like nitrogen and oxygen. However, the story for planets like super-Earths and mini-Neptunes becomes more complicated when we look at their mass, size, and atmospheric compositions. Super-Earths and mini-Neptunes sit at an interesting middle ground, with masses larger than Earth's but smaller than Neptune. These planets are large enough to potentially attract significant amounts of gas, but they are not massive enough to retain a massive hydrogen and helium envelope like gas giants. This has led scientists to propose that super-Earths and mini-Neptunes may form through different processes than smaller terrestrial planets like Earth. One theory is that these planets might form from the same building blocks as Earth but accrete more material, growing into larger planets. Once they reach a certain size, their gravity may capture and retain a thick atmosphere of hydrogen and helium, creating the mini-Neptune-like characteristics we observe. Alternatively, they could form through the accumulation of ices and gases in the outer regions of the protoplanetary disk, leading to larger, gas-rich planets. The diversity of atmospheres around these planets also raises questions about their internal structures. While Earth-like planets are largely made of rock and metal, super-Earths and mini-Neptunes may have a more complex layering system. Some may have solid, rocky cores surrounded by thick gaseous layers, while others might be made up of a combination of water, ice, and rock. This variation in composition is largely influenced by a planet's size, distance from its host star, and the amount of material available in the protoplanetary disk from which it formed. One of the most intriguing aspects of super-Earths and mini-Neptunes is how their atmospheres interact with their host stars. These planets are often located in the habitable zone of their star, where liquid water could potentially exist on their surfaces. However, their atmospheres play a crucial role in regulating surface temperatures and creating the conditions necessary for life. In some cases, these atmospheres may be too thick or too thin to support liquid water, and the surface conditions could be inhospitable. However, in other cases, these atmospheres may provide the perfect conditions for life, acting as a greenhouse and trapping enough heat to keep water in liquid form. The study of super-Earths and mini-Neptunes also brings attention to the possibility of volcanic activity on these planets. As we look at our own solar system, we see that volcanic activity has been a key driver of the development of planetary atmospheres and the potential for life. On Earth, volcanic eruptions release gases like carbon dioxide, sulfur, and water vapor into the atmosphere, which play a critical role in regulating the planet's climate and supporting life. On super-Earths and mini-Neptunes, volcanic activity could have a similar impact, potentially contributing to the development of habitable conditions. While these planets may have characteristics that make them seem inhospitable on the surface, there is still much that we do not know about their internal processes. Some scientists believe that there could be hidden oceans beneath thick atmospheres, or that liquid water may exist in underground reservoirs, potentially providing a safe haven for life. The discovery of life on Earth in extreme environments, such as deep-sea hydrothermal vents, has shown us that life can thrive in places we would never have imagined. It's possible that super-Earths and mini-Neptunes could harbor life in environments that are completely alien to us, hidden beneath their thick clouds or beneath the surface. In terms of habitability, we also need to consider the relationship between super-Earths and mini-Neptunes with their parent stars. These planets may orbit their stars at different distances, which can greatly affect their surface temperatures and the amount of radiation they receive. Some super-Earths may be close enough to their stars to experience extreme heat, making them unsuitable for life as we know it, while others may be far enough to maintain more temperate climates. Mini-Neptunes, on the other hand, are often located in regions where they are exposed to intense radiation, which could strip away their atmospheres over time, leaving them barren and lifeless. The fact that we've discovered so many of these planets suggests that our understanding of the formation and evolution of planetary systems is still in its early stages. As we discover more exoplanets and continue to refine our techniques for studying distant worlds, we are likely to learn more about the processes that lead to the creation of super-Earths and mini-Neptunes. With more powerful telescopes like the James Webb Space Telescope, we will be able to study these planets in more detail, examining their atmospheres, temperatures, and potential for life. One of the most exciting aspects of studying super-Earths and mini-Neptunes is the possibility of discovering new forms of life. While the search for Earth-like planets that could host life has dominated much of the conversation around exoplanets, the discovery of these unique planets forces us to reconsider our assumptions about what makes a planet habitable. If life can exist in environments that are vastly different from Earth's, it could expand our understanding of biology and the possibilities for life beyond our solar system. In many ways, super-Earths and mini-Neptunes are a glimpse into the future of planetary exploration. As we continue to explore these strange new worlds, we may discover more about the fundamental processes that govern the formation of planets and the conditions that allow life to thrive. These planets may hold the answers to some of the most profound questions about our place in the universe. Are we truly alone, or are there other forms of life out there waiting to be discovered? By studying super-Earths and mini-Neptunes, we are one step closer to answering this age-old question. As we wrap up our exploration of these fascinating planets, one thing is clear: the universe is filled with mysteries, and super-Earths and mini-Neptunes are among the most intriguing. These strange new worlds may hold the key to unlocking some of the greatest mysteries of planetary formation, habitability, and life beyond Earth. The more we learn about them, the more we realize just how much there is still to discover. As we continue to unravel the mysteries surrounding super-Earths and mini-Neptunes, another key factor to consider is the role of atmospheric escape. This phenomenon happens when a planet's atmosphere is gradually lost to space over time, and it's especially relevant to understanding how these planets evolve and why some may not retain their atmospheres in the long term. For super-Earths, which tend to be significantly more massive than Earth, atmospheric escape can still occur, but it's generally a slower process compared to smaller, less massive planets. However, the rates of atmospheric loss can depend on factors such as stellar radiation, the presence of a magnetic field, and the composition of the atmosphere itself. For instance, planets that orbit close to their stars receive more intense radiation, which can heat up their atmospheres, causing lighter gases like hydrogen and helium to escape into space. In some cases, this might lead to a loss of the lighter gases while retaining heavier elements like carbon dioxide and oxygen, potentially allowing these planets to evolve into habitable environments. On the other hand, Mini-Neptunes, with their thick hydrogen and helium-rich atmospheres, are more susceptible to atmospheric stripping. If these planets orbit too close to their parent stars, they may experience what's known as photoevaporation, where ultraviolet radiation from the star causes the outer layers of the atmosphere to evaporate over time. This process can strip away significant portions of a mini-Neptune's atmosphere, turning it into a more rocky, barren world over billions of years. However, if a mini-Neptune is far enough from its star, it might be able to retain its thick atmosphere, which could potentially harbor gases that are crucial for sustaining life. The question of whether super-Earths and mini-Neptunes could support life hinges largely on the composition of their atmospheres. Planets with thick atmospheres that are rich in greenhouse gases like carbon dioxide or methane could experience a runaway greenhouse effect, where temperatures rise to uninhabitable extremes. This has been hypothesized for some super-Earths, particularly those in close orbits around their stars. However, if these planets are far enough from their stars, they might be able to maintain more temperate climates, with stable conditions that could support the development of life. Mini-Neptunes, with their vast atmospheres, also pose an interesting case. Their thick cloud layers could trap heat, creating surface temperatures that are conducive to the presence of liquid water, a key ingredient for life as we know it. However, as mentioned earlier, the eventual loss of their atmosphere could leave them as cold, desolate worlds. The potential for life on these planets, therefore, might depend on whether their atmospheres are stable enough to provide long-term, habitable conditions. Beyond just understanding the physical attributes of these planets, scientists are also looking at their potential for hosting alien life. While Earth-like planets have long been the focus of the search for extraterrestrial life, super-Earths and mini-Neptunes have now become important areas of study. The discovery of exoplanets that exist in the habitable zone, also known as the Goldilocks zone, of their stars, where conditions are just right for liquid water to exist, has sparked much interest. While some of these planets may have hostile environments, others may present a more hopeful view. One of the ways that astronomers are trying to learn more about the habitability of these planets is through the study of their atmospheres. Instruments like the James Webb Space Telescope, JWST, are designed to study the atmospheres of distant exoplanets by observing the light that passes through them. This allows scientists to detect the chemical composition of these atmospheres and look for signs of habitability, such as water vapor, carbon dioxide, and other gases that might suggest the presence of life. The study of atmospheric composition is particularly important when it comes to understanding the evolution of super-Earths and mini-Neptunes. For example, planets with a thick atmosphere might have a different climate than planets with a thin atmosphere, even if they are located in the same region of the habitable zone. By comparing the atmospheres of these planets, scientists can learn more about how atmospheric conditions influence the potential for life and how planets evolve over time. Another fascinating aspect of super-Earths and mini-Neptunes is their potential to help us better understand the conditions required for planetary habitability in general. The sheer variety of exoplanets we've discovered, each with its own unique set of characteristics, challenges the long-standing assumptions we had about what makes a planet habitable. Super-Earths and mini-Neptunes, with their diverse sizes, compositions, and orbits, force us to reconsider what types of environments might support life. For instance, it was once thought that only planets with similar characteristics to Earth would be capable of hosting life. However, the discovery of worlds with vastly different conditions, such as super-Earths and mini-Neptunes, opens up new possibilities for life beyond our solar system. These planets may provide a different kind of Goldilocks zone, where life could survive under conditions we would not have previously considered. The study of these planets also brings us closer to answering some of the most profound questions about the universe. How did planetary systems form? And why do some planets end up as super-Earths or mini-Neptunes while others stay small and rocky? What conditions allow life to flourish? And what factors make a planet inhospitable? By continuing to study these strange new worlds, we are not only learning more about how planets form, but we are also gaining new perspectives on what it means for a planet to be habitable. In the future, we may even begin to identify planets that share some of the same characteristics as Earth. Super-Earths and mini-Neptunes may serve as stepping stones in our search for Earth-like planets, providing clues about the kinds of environments where life could potentially exist. By studying the atmospheres, climates, and internal structures of these planets, we might one day discover a world that mirrors Earth in ways we've only dreamed of. Another exciting possibility is that future missions might one day visit or even land on planets within our own solar system that have characteristics similar to those of super-Earths and mini-Neptunes. While current technology makes it difficult to directly explore exoplanets, future advancements in space travel could open up new opportunities for exploring distant worlds. With missions to the outer planets and beyond, we could gain even more insights into the formation of these planets and their potential for habitability. As the search for new exoplanets continues to progress, we are likely to discover even more super-Earths and mini-Neptunes, each with its own set of mysteries. These planets are still relatively new to science, and much remains to be uncovered about their origins, compositions, and potential for hosting life. The discovery of these planets represents just the beginning of a new era in the study of exoplanets, and they hold the key to some of the most exciting questions in astronomy today. The more we learn about these strange new worlds, the closer we come to understanding the true nature of planetary systems, the conditions that make a planet habitable, and the potential for life beyond Earth. Super-Earths and mini-Neptunes may not be our best chance for discovering life in the universe, but they are certainly an essential piece of the puzzle. As we continue to push the boundaries of our knowledge, there is no telling what other incredible discoveries await us in the vast expanse of space. These enigmatic planets, with their unique characteristics and potential for habitability, are a reminder of just how much there is still to learn about the universe we call home. The study of super-Earths and mini-Neptunes isn't just about uncovering the possibility of life elsewhere in the universe. It also serves as a crucial piece of the puzzle in understanding how planetary systems evolve. These planets, often located in distant star systems, reveal a lot about the forces at play during planetary formation, migration, and atmospheric development. Take, for example, the role of migration. During the early stages of planetary system formation, planets often don't stay in the orbits they start with. Instead, they can migrate, often moving closer to or farther from their star. Super-Earths and mini-Neptunes offer compelling evidence of this process. By studying their current positions, scientists can trace back their possible migratory paths and get a better idea of how planetary systems evolve over time. Some of these planets have been found in surprising locations, which suggests that migration is not just a random occurrence, but a fundamental aspect of planetary formation. For instance, super-Earths are sometimes found in the inner parts of their solar systems, close to their stars, where they should not have been able to form in the first place, given how rocky planets are thought to develop. The fact that these planets exist in such orbits suggests that something must have pushed them inward from farther out regions. This discovery challenges previous models of planetary system formation and forces scientists to rethink how planets migrate across their orbits. The understanding of planetary migration has wide-reaching implications, not only for the study of exoplanets but also for our own solar system. It could explain the existence of certain planetary features we see in our own backyard, such as the irregular orbits of some asteroids and the peculiarities of the outer planets. If migration happens on a large scale, it could help explain why the outer planets, like Neptune and Uranus, have such distant and unusual orbits. The continued study of these planets, their migration, and their place in their star systems is vital for creating a more comprehensive theory of planetary system formation. As we gather more data about the orbits and compositions of super-Earths and mini-Neptunes, we'll be able to refine our models of how the universe creates planets and how those planets evolve. Looking beyond their potential for life or scientific value, super-Earths and mini-Neptunes also challenge our conception of what a normal planet should be. Earth, with its rocky composition, liquid water, and temperate climate, is often the benchmark by which we measure other planets. However, as we discover more exoplanets in the size range of super-Earths and mini-Neptunes, it becomes clear that there is no one-size-fits-all model for planets. These planets, while somewhat similar to Earth in size, are vastly different in other ways, showing that planets come in a variety of forms and that there are many different ways for a planet to evolve and exist. In fact, these findings have spurred a shift in how we approach the search for habitable planets. We've spent decades focused primarily on finding Earth-like planets in the Goldilocks zone. However, as more super-Earths and mini-Neptunes are discovered, it becomes evident that we must expand our criteria for what makes a planet suitable for life. The diversity of these planets means that life might exist in ways we hadn't even considered, possibly on planets that don't resemble Earth at all. The possibility that life could arise in completely different conditions, like those found on some super-Earths or mini-Neptunes, opens up a new frontier in the search for extraterrestrial life. Another factor to consider in this conversation is the growing technological advancements that are allowing us to peer deeper into space and study these distant planets in unprecedented detail. The current generation of space telescopes, such as the James Webb Space Telescope, is providing us with the tools needed to study the atmospheres of exoplanets in greater detail than ever before. This advancement is allowing astronomers to analyze the chemical compositions of the atmospheres of super-Earths and mini-Neptunes, searching for clues about their potential to support life or their unique evolutionary history. These atmospheric analyses are providing us with exciting data about the kinds of environments that exist on distant worlds. For example, we are now able to detect water vapor, methane, and carbon dioxide in the atmospheres of exoplanets, all of which are essential ingredients for life as we know it. The discovery of these substances on super-Earths and mini-Neptunes could be one step closer to finding signs of life beyond Earth, even if that life looks very different from what we might expect. Moreover, as we continue to refine our techniques for observing exoplanets, the number of planets we can study increases. This allows for a broader statistical approach to understanding what kinds of environments might be conducive to life. In the near future, we could have enough data to compare planets across a range of sizes and types, such as super-Earths, mini-Neptunes, and more Earth-like planets, to draw definitive conclusions about the conditions necessary for life to thrive. These advancements also underscore the importance of studying a wide variety of planets in different star systems. The more planets we study, the more we can understand the nuances of planetary systems and how various factors, such as the star's radiation, the planet's size, and its atmospheric composition, affect the potential for life. Super-Earths and mini-Neptunes, with their unique characteristics, offer the perfect opportunity to study these factors in depth. As we continue our exploration of these enigmatic planets, it's clear that the search for super-Earths and mini-Neptunes will play a key role in advancing our understanding of not only the potential for life beyond Earth but also the fundamental processes that govern planetary formation. By studying the diversity of these planets, we can learn more about the forces that shape planets throughout the galaxy and how those forces might lead to worlds capable of supporting life. What makes these planets especially fascinating is the sheer variety of possibilities they present. While some super-Earths may be too hot and hostile to support life, others could have temperate climates, with oceans and land masses where life might flourish. Similarly, mini-Neptunes with thick atmospheres could harbor conditions favorable for life, or their atmospheres could eventually be stripped away, leaving behind barren, rocky worlds. The true extent of what we will learn from super-Earths and mini-Neptunes is still unfolding, and each new discovery takes us one step closer to answering the most fundamental questions about our place in the universe. As our tools and methods for exploring these distant planets continue to improve, the future of exoplanet research looks incredibly promising. Super-Earths and mini-Neptunes, strange as they may seem, are poised to revolutionize our understanding of how planets form, evolve, and potentially support life. These planets offer us a tantalizing glimpse into the diversity of worlds that exist beyond our solar system. Their existence challenges our assumptions about what a planet can be and what it takes for a world to host life. Through continued exploration and study, we may discover that the universe is far more varied and full of potential than we ever imagined. As we continue to explore these strange new worlds, it's important to highlight how studying super-Earths and mini-Neptunes may also change our perspective on Earth itself. For a long time, Earth was viewed as the model for habitable planets, with our atmospheric conditions, liquid water, and distance from the Sun being seen as ideal for sustaining life. However, the discovery of exoplanets like super-Earths and mini-Neptunes pushes us to reconsider what conditions might truly be required for life to thrive. For example, some super-Earths are much closer to their stars than Earth is to the Sun, which means their atmospheres might be subjected to much higher radiation levels. This might seem inhospitable at first glance, but it's possible that these planets could have evolved with unique forms of life that are adapted to extreme conditions. This challenges the notion that life can only survive in environments similar to Earth's. It expands the possibilities of what habitability could look like across the cosmos, forcing us to think beyond our limited understanding of what life needs to survive. Furthermore, by studying the size and structure of super-Earths and mini-Neptunes, we can also learn about the history of planetary migration. Many of these planets are located far from where scientists initially thought such large planets could form. They could have migrated inward from farther reaches of their star systems, which raises questions about how such planets came to be where they are now. This process of planetary migration can tell us a lot about the dynamic and often chaotic early stages of a planetary system's development. In our own solar system, the planets have relatively stable orbits. Earth, for example, has remained in the same general position in relation to the Sun for billions of years. However, in other star systems, planets may not always be as stable. Super-Earths and mini-Neptunes, which may have started farther out in their star systems before migrating inward, offer a window into this chaotic, early phase of planetary development. Their current positions could be the result of complex interactions between planets, stars, and other cosmic forces. This concept of planetary migration is not only important for understanding exoplanets, but could also offer insights into the history of our own solar system. For instance, the unusual orbits of some outer planets, like Neptune and Uranus, could have been influenced by similar migratory processes. If these distant giants once formed closer to the Sun and then migrated outward, it could explain some of the strange dynamics we observe in our solar system today. Another aspect of super-Earths and mini-Neptunes that warrants attention is their potential for hosting moons. While many of these planets are quite large, the presence of moons could dramatically alter the potential habitability of these worlds. Moons can stabilize a planet's axial tilt, which can have a significant impact on the climate. For example, a large moon might help maintain a relatively stable climate on a planet by preventing its axis from wobbling too much. This is why Earth's moon is so crucial to our own planet's climate stability. Additionally, moons can create diverse environments of their own, potentially harboring conditions suitable for life. Some of the moons in our solar system, like Jupiter's Europa or Saturn's Enceladus, have shown evidence of subsurface oceans beneath their icy crusts. If similar moons exist around super-Earths or mini-Neptunes, these oceans could provide the ideal conditions for life to emerge and thrive. The discovery of moons around these types of exoplanets would also tell us more about how planetary systems form. Some theories suggest that moons are created when material from the planet's protoplanetary disk clumps together to form satellites. Studying the moons of super-Earths and mini-Neptunes could provide clues about the composition and evolution of planetary systems far beyond our own. In addition to the study of moons, another area of research that has garnered attention is the potential for ring systems around super-Earths and mini-Neptunes. Our solar system's gas giants, like Saturn and Jupiter, are known for their iconic ring systems. It's possible that exoplanets of similar sizes could also have rings, adding an additional layer of complexity to their structure. The presence of rings could provide valuable information about the planet's history and the forces that shaped its current form. What's fascinating is that these ring systems could also offer insight into the age of a planet. Some scientists speculate that the rings around planets like Saturn could be relatively short-lived, only existing for a few 100 million years before being absorbed into the planet or scattered into space. If a super-Earth or mini-Neptune has rings, studying those rings could help scientists determine the age of the planet, providing a timeline for its formation and evolution. As technology improves, we are also learning more about the potential for volcanic activity on these distant worlds. Volcanism is an important process in planetary evolution, as it can contribute to the creation of atmospheres, the recycling of materials, and even the formation of oceans. Super-Earths, with their larger sizes, might have intense volcanic activity, especially if they have high levels of internal heat. This activity could contribute to the formation of thick atmospheres, rich in gases like carbon dioxide and methane. Such volcanic outgassing could even provide clues to the planet's potential for habitability, or its ability to support life. Mini-Neptunes, with their thick, gaseous envelopes, could also provide a unique opportunity for studying planetary volcanism. While the surface of a mini-Neptune might be unreachable, understanding the dynamics of its internal heat and any possible volcanic activity could provide new insights into how gas giants and ice giants evolve over time. Even more exciting is the possibility of volcanic activity occurring on moons of these planets, where conditions might be more favorable for the development of life. Finally, let's consider the broader implications of studying super-Earths and mini-Neptunes for humanity's understanding of the universe. The search for life beyond Earth has long been a driving force in space exploration, but these strange planets remind us that the universe is vast, and the conditions that might support life are not as straightforward as we once believed. The diversity of exoplanets we are discovering, especially super-Earths and mini-Neptunes, suggests that the cosmos is filled with worlds that have unique characteristics, and perhaps even unique forms of life. By studying these planets, we not only expand our understanding of where life might exist but also learn more about how planets form, evolve, and interact with their stars. In turn, this knowledge will help us refine our theories about the history of our own planet and its future. It will also guide the search for other habitable worlds in our galaxy, giving us a better idea of what to look for and how to find it. As we continue to develop the technology to observe these distant planets and gather more data, the future of exoplanet research holds tremendous promise. Super-Earths and mini-Neptunes, with all their strange and fascinating features, offer a treasure trove of information that could change our understanding of the cosmos. They serve as a reminder that even in the vastness of space, there is still much to be discovered and understood. The potential for discovery on super-Earths and mini-Neptunes extends beyond the exploration of their atmospheres, moons, and rings. These planets also provide us with a rare glimpse into the mechanics of planetary composition, magnetic fields, and their interactions with stellar winds, all of which can play a major role in their potential to support life or undergo radical transformation over time. Let's first take a closer look at the magnetic fields of these planets. Our own Earth's magnetic field plays a crucial role in protecting us from harmful solar radiation. It acts as a shield that diverts charged particles from the Sun, ensuring that life can survive on the surface without being bombarded by dangerous radiation. For a super-Earth or mini-Neptune, the strength and composition of their magnetic field could be a determining factor in their ability to support life. Super-Earths, with their larger sizes, might have more powerful magnetic fields, particularly if they are rich in metals like iron and nickel. These materials could help generate a strong magnetic shield around the planet, potentially making them more habitable for life by blocking out harmful solar winds. However, a strong magnetic field isn't necessarily a guarantee of habitability. Some planets might have magnetic fields that fluctuate in strength, or they might have magnetic poles that are unstable, creating drastic fluctuations in the amount of radiation that reaches the surface. Mini-Neptunes, on the other hand, are mostly gaseous, with thick atmospheres that may limit the extent to which they can generate magnetic fields in the same way as rocky super-Earths. Still, it is possible that some mini-Neptunes could possess strong magnetic fields, especially if they have a rocky core that could support the necessary geological processes to generate such fields. These planets might also offer clues about the development of planetary magnetic fields in gas giants, and how these fields evolve over time. Understanding the magnetic fields of super-Earths and mini-Neptunes can also give scientists valuable insights into how planets interact with their host stars. Stellar winds, which are streams of charged particles emitted by stars, can strip away the atmosphere of a planet if the planet's magnetic field is too weak to protect it. This process, known as atmospheric erosion, could lead to the gradual loss of essential components like water vapor or carbon dioxide, which are crucial for life. In the case of super-Earths, the strength of their magnetic fields could be a key factor in determining whether they retain their atmospheres or lose them over time. For example, if a super-Earth orbits close to its star, it might experience intense stellar winds, and if the planet's magnetic field isn't strong enough, it could lose significant portions of its atmosphere. Conversely, if the magnetic field is strong, it could shield the atmosphere and keep the planet in a habitable state for much longer periods. For mini-Neptunes, the impact of stellar winds could be even more dramatic. Their thick atmospheres are already composed of gases like hydrogen and helium, and stellar winds might strip away the outer layers of these gases, leaving behind the rocky core. This process could reveal hidden insights into the planet's formation and evolution, potentially providing a glimpse into how other gas giants like Jupiter and Saturn in our own solar system might have evolved from smaller, rocky bodies into the massive planets we see today. One of the most fascinating aspects of studying super-Earths and mini-Neptunes is the potential for detecting signs of alien life. While the possibility of life on these planets might seem far-fetched at first, the search for biosignatures, chemical or physical markers that indicate the presence of life, has become one of the central goals of exoplanet research. In fact, the discovery of super-Earths and mini-Neptunes has shifted our focus to planets that are slightly larger than Earth, but that still have the potential to harbor conditions that could support life. On super-Earths, the larger size and higher gravity may result in more volcanic activity, which could release gases like carbon dioxide and methane into the atmosphere. These gases could potentially create conditions that are conducive to life, especially if the planet is located within the habitable zone of its star. The habitable zone is the region around a star where conditions are just right for liquid water to exist on the surface of a planet. Even if the planet's surface is rocky or volcanic, the right balance of atmospheric gases could help maintain the temperature necessary for liquid water. Mini-Neptunes, on the other hand, present a different set of challenges and opportunities when it comes to the search for life. While these planets are largely gaseous, they may have moons that could harbor subsurface oceans. If one of these moons has the right chemical composition, it could host life in the same way that Europa or Enceladus, moons of Jupiter and Saturn, have been considered potential places for extraterrestrial life to exist. The discovery of such moons orbiting mini-Neptunes could open entirely new possibilities for finding life in the universe. Moreover, the detection of biosignatures on super-Earths and mini-Neptunes would require advanced observational techniques and instruments. The James Webb Space Telescope, set to launch in the near future, is expected to revolutionize the study of exoplanets by allowing scientists to examine the atmospheres of distant worlds in unprecedented detail. By analyzing the chemical composition of these atmospheres, scientists can look for signs of oxygen, methane, and other molecules that might be associated with biological processes. The presence of such molecules could be a telltale sign that life is present or was once present on a planet. Additionally, the study of exoplanetary atmospheres can help scientists understand the potential for terraforming, transforming a planet to make it more habitable for humans or other forms of life. Super-Earths, with their larger sizes, might be easier to terraform than smaller, rocky planets, as they have greater mass and could potentially retain their atmospheres for longer periods. Mini-Neptunes, on the other hand, may be more challenging to terraform due to their thick atmospheres and lack of a solid surface. However, studying these planets can still provide valuable insights into the limits of planetary habitability, and what factors would need to be adjusted in order to make a planet more Earth-like. In addition to the search for life, the study of super-Earths and mini-Neptunes is critical to understanding the broader question of planetary formation. Most of the planets in our solar system fall into one of two categories: rocky planets like Earth, Venus, Mars, and Mercury, or gas giants like Jupiter and Saturn. Super-Earths and mini-Neptunes challenge this neat division, offering a new type of planet that doesn't fit easily into either category. Super-Earths are likely formed through a process known as core accretion, in which a planet starts with a small solid core that gradually accumulates gas from the surrounding nebula. The result is a planet that is larger than Earth but still has a solid surface. These planets may share some characteristics with Earth, such as the potential for liquid water, but their greater size and mass can lead to a vastly different evolutionary path. Mini-Neptunes, on the other hand, are thought to form through a process known as disk instability. In this scenario, a large clump of gas and dust in a protoplanetary disk rapidly collapses under its own gravity, forming a planet that is mostly gas with a small solid core. Mini-Neptunes are generally smaller than the gas giants in our own solar system, but they still present important questions about how gas giants form and whether they can support moons that might harbor life. By studying these two types of planets, scientists can refine their models of planetary formation and gain a better understanding of how planets evolve over time. Whether through migration, volcanic activity, or the development of magnetic fields, super-Earths and mini-Neptunes provide us with a rich source of information that could reveal new insights into the processes that govern the birth and life of planets throughout the universe. The discoveries of super-Earths and mini-Neptunes mark a new era in the exploration of exoplanets, where the line between the familiar and the strange is continuously blurred. These worlds are not just larger or smaller versions of Earth, but entirely new kinds of planets that defy easy categorization. Their study challenges our assumptions about what planets can be, how they form, and what makes them habitable. They may ultimately teach us not only about the diversity of planets in the universe but also about the very nature of our own planet, and what it means for Earth to be special. The discovery of super-Earths and mini-Neptunes is nothing short of revolutionary in the world of astronomy and planetary science. While we have learned a great deal about our own solar system, these new planets, found orbiting distant stars and galaxies far beyond our own, continue to push the boundaries of our understanding of what is possible in the realm of planetary formation, evolution, and the potential for life. As we look to the future, these types of exoplanets will not only challenge our existing models but may also present new avenues for exploration, both in terms of the tools we use to study them and the hypotheses we form about their nature. One of the most pressing questions when it comes to super-Earths and mini-Neptunes is, what can these planets teach us about the broader dynamics of planetary systems? For example, how do they influence the development of other planets within their respective star systems? One possibility is that these planets play a critical role in regulating the stability of their star systems, particularly when it comes to the distribution of smaller, rocky planets like Earth. If super-Earths and mini-Neptunes are more common than we once believed, they may help explain the phenomenon of planetary migration, the process by which planets shift their orbits over time due to gravitational interactions with nearby planets or their star. This is particularly important when studying star systems that feature planets with strange orbits or characteristics that seem unusual compared to those in our own solar system. Super-Earths, with their larger masses, could exert significant gravitational forces on smaller planets, pulling them into different orbits and affecting their stability. Such interactions may explain some of the unusual orbital patterns we see in exoplanets. Furthermore, some astronomers believe that super-Earths could be failed gas giants, planets that started forming in a similar way to Jupiter or Saturn but were unable to gather enough material to become full-fledged gas giants. This raises the question of whether there are many more gas giants waiting to be discovered, planets that are too distant or too small to meet our traditional criteria for categorization, but that still share many of the same properties as their larger counterparts. By studying super-Earths, we might be able to piece together the evolution of these gas giants, refining our models of how planets like Jupiter and Saturn came to be. Mini-Neptunes, in contrast, represent a different category of planet altogether, one that challenges our preconceptions of planetary evolution. While super-Earths may have an Earth-like surface, albeit much larger, mini-Neptunes are more gaseous and resemble Neptune in many ways, with thick atmospheres that often contain hydrogen and helium. They might, however, differ in how they maintain their atmospheres. For example, some mini-Neptunes could be in the process of losing their atmospheres entirely due to their proximity to their stars, while others might be slowly accumulating more material, expanding into more massive planets over time. In fact, the study of mini-Neptunes has prompted scientists to rethink the idea of planetary evaporation. While it was once believed that small planets could not hold onto thick atmospheres for long, mini-Neptunes challenge that assumption by maintaining their gaseous envelopes for extended periods. This raises the question of whether some of these planets may eventually evolve into something entirely different over billions of years, shedding their gaseous layers and becoming rocky super-Earths, or even evolving into something entirely new and unforeseen in terms of planetary characteristics. One of the most intriguing aspects of these planets is their potential for habitability. While we may think of the search for life as being synonymous with planets similar to Earth, such as those in the habitable zone, where liquid water can exist on a planet's surface, the unique environments found on super-Earths and mini-Neptunes could also be worth exploring. Even though these planets might not be Earth-like in the traditional sense, they may still offer clues about the wider range of conditions that life could thrive in, or at least survive in, throughout the cosmos. In fact, some researchers have suggested that life could exist on moons of super-Earths or mini-Neptunes, particularly if those moons have subsurface oceans, as is the case with moons like Europa and Enceladus in our own solar system. These moons would be shielded from the harsh conditions of their host planets by their thick atmospheres, which could potentially provide protection from harmful radiation and other hostile elements. If such moons are located within their host planet's habitable zone, it's conceivable that they could harbor life, potentially even life forms that are radically different from anything we recognize. Moreover, the atmospheres of these planets might reveal much about their potential for life. For example, a planet's atmosphere can tell us a great deal about its composition, weather patterns, and whether it experiences conditions that are conducive to life. Some scientists are already investigating the possibility that, through a combination of carbon dioxide, methane, and water vapor, super-Earths could maintain the right balance of chemicals to support life. Mini-Neptunes, on the other hand, present a more complex puzzle, as their atmospheres might be rich in gases like hydrogen and helium, which would make it difficult for life to survive on the surface without significant environmental intervention. This complexity makes the study of super-Earths and mini-Neptunes particularly important as we refine our models of habitability. If life does not exist on these planets, it doesn't necessarily mean that life is only possible on Earth-like worlds. Instead, these exoplanets could provide us with a broader framework for understanding the diverse ways in which life could emerge in the universe. Just as Earth's history shows that life can thrive in environments once thought inhospitable, from the deepest ocean trenches to the driest deserts, the study of super-Earths and mini-Neptunes challenges our assumptions about where life can exist. There's also the possibility that these planets could teach us about the limits of planetary habitability. By examining planets with different sizes, compositions, and atmospheres, scientists can gain insights into what makes a planet truly habitable, and what might make a planet uninhabitable. For instance, it is possible that planets like super-Earths might have more extreme volcanic activity due to their size, making them less likely to be hospitable to life. Similarly, mini-Neptunes might be so far removed from the habitable zone of their star that any potential for life would be negligible, even if their moons are more favorable. In the coming decades, the tools we have at our disposal to study these mysterious planets will continue to evolve. Telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope will allow us to peer deeper into space and gather more detailed information about the atmospheres and compositions of exoplanets. In doing so, we will likely uncover even more surprising features of these planets, from strange weather patterns to mysterious magnetic fields, and will continue to refine our models of how planets form and evolve. Super-Earths and mini-Neptunes are, without a doubt, some of the most fascinating exoplanets we have discovered in recent years. Their sheer diversity, from rocky worlds with the potential for life to massive gas planets with strange atmospheric dynamics, challenges everything we thought we knew about how planets form, evolve, and interact with their stars. With each new discovery, we come closer to understanding the complex and dynamic processes that govern not only the planets in our own solar system, but also the many worlds that exist beyond it. In exploring these worlds, We are not only expanding our knowledge of distant planets, but also pushing the limits of human curiosity. Every new planet discovered, whether it's a super-Earth or a mini-Neptune, brings us one step closer to answering some of the most profound questions we can ask. Are we alone in the universe? What else is out there? And how did our own planet come to be? As the study of exoplanets continues to evolve, super-Earths and mini-Neptunes will undoubtedly play a key role in shaping the future of planetary science, offering clues about everything from the formation of planets to the potential for life in the universe. These strange new worlds are more than just distant objects in the sky. They are a window into the complexity and wonder of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.